In this video, we're gonna cover the mole concept. So let's start with the motivation for the mole. Let's say you're a chemist who's trying to react a compound A with a compound B to create a complex A, B. Now, this reaction is called a one-to-one reaction because one particle of A reacts with one particle of B to create one particle of complex AB. So let's suppose we want 5 grams of AB. How many grams of A do we need and how many grams of B do we need? Judging from the equation, it might be natural to suggest that you need 2.5 grams of A and 2.5 grams of B. But this is actually not the case. And this is because particles have different mass. For example, one particle of helium would weigh much less than one particle of gold. This is the motivation of the mole concept. If we know that we want a certain amount of particles, we want to know how many grams of a substance we need to reach this number of particles. So let's write that the motivation is to relate number of particles with mass. Let's think about an intuitive way to relate number of particles to mass. So we know that all atoms are comprised of protons, neutrons, and electrons. So we would therefore ideally relate mass to the number of protons, neutrons, or electrons. But let's first look at the mass of the different particles. So the rest mass of an electron is approximately 9.1 times 10 to the minus 31. The rest mass of a neutron is approximately 1.7 times 10 to the minus 27. And the rest mass for a proton is the same, or approximately the same. So from here we see that the rest mass of an electron is almost 1000 times less than the rest mass of a proton or neutron. And this means that you need 1000 electrons to get the same mass as a proton or neutron. And since this almost never happens, or it doesn't happen in chemistry when it comes to atoms, so we just say that we don't care about electrons when relating atoms to mass. So we're left with protons and neutrons. What do we want to do with protons or neutrons? So what we want is to know how many protons or neutrons you need to get 1 gram. So let's say that we need X particles, that X particles of protons or neutrons equals 1 gram. From this we can know that if, well, for example, helium, which has 4 or has 2 protons and 2 neutrons. From this we can know that if we have X particles of helium, we would have X, or we have 2X protons and 2X neutrons. So this would be 4 grams. So in this way we could relate the number of particles to mass. And since we have related the number of particles to mass with a very fundamental particle in chemistry, this would apply to all the elements. We now just need to know how many particles of protons or neutrons we need to get 1 gram. And the person who figured this out was named Avogadro. And what he found out was that you needed 6.02 times 10 to the 23rd number of particles of protons and neutrons to reach 1 gram. And this is such an important number that it even got its own name, and it's called Avogadro's number. More importantly is that Avogadro's number relates to a unit, and this unit is the mole, which is denoted MOL. So the mole becomes 6.02 times 10 to the 23 number of particles. which is the same as Avogadro's number of particles. Let's visualize how to relate particles to moles with a diagram where we have particles on one side and moles on another side. So how do we go from particles to moles, and how do we go from moles to particles? A top tip for science subjects in general is to consider the units. So let's look at the units for Avogadro's number. We know that Avogadro's number is 6.02 times 10 to the 23rd, and the units are particles per mole, which is denoted as mole to the power of -1. So let's now say that we have x mole, and we want to know how many particles we have. So we need to make this expression cancel out mole, so we end up with particles. And in this case, it's pretty easy. We just multiply by Avogadro's number with the units particles per mole. Now we can see that the unit of mole cancels out because it's mole divided by mole. So we're just left with x times 6.02 times the 10 to the power of 23 particles. So we now just converted moles into particles by multiplying by Avogadro's number. So multiply by 6.02 times 10 to the 23rd. So if this is the case when you turn moles to particles, the opposite must be the case to turn particles into moles. So we can already say that you just need to divide by 6.02 times 10 to the 23rd. To confirm that this is the case, we can consider the units again. So let's say we have x particles, and we want to see how many moles we have. So what we do is that we divide by Avogadro's number with the units particles per mole. So we see immediately that particles cancels out, and we're left with x over 6.02 times 10 to the 23rd per mole. And the units here are 1 divided by per mole, which is the same as 1 divided by 1 over mole. And you should know that if you divide by fraction, you just flip it. So this becomes mole over 1, which is just moles. So we just confirm that if you want to go from particles to moles, you just divide by Avogadro's number. Now, how does the mole relate to mass? To understand this, we can consider the definition of the mole. And the definition is the number of carbon atoms in 12 grams of carbon-12. So let's think about this. Carbon-12 has 6 protons because it's carbon, and 6 neutrons because the number of protons and neutrons has to add up to 12. And we also know that 1 mole of protons or neutrons equals 1 gram. So since we have 1 mole of carbon-12, it means that we have 6 moles of protons and 6 moles of neutrons. So 1 mole of carbon-12 equals 12 grams. So in this way we can relate moles and grams. From the definition, we saw that 1 mole of carbon-12 has a mass of 12 grams. And we figured this out because carbon-12 is made of 6 protons and 6 neutrons. And since all the elements are made of protons and neutrons, we can assign a mass number to 1 mole of any element. For example, 1 mole of hydrogen 1 would be 1 gram. 1 mole of helium 4 would be 4 grams, and so on. Now this is a very important observation because we just figured out a way to turn moles into mass. And this property has its own name, and it's called the molar mass, which is usually denoted as a big M. Let's see how moles relates to mass by making the same type of diagram, where we have moles on this side and mass on this side. How do we go from moles to mass, and how do we go from mass to moles? Let's consider the units of molar mass. Let's consider the units of molar mass. So molar mass has the unit grams per mole. So let's say that we have X moles of something, and we want to convert this into mass. And this means that we want the unit mole to cancel out, so that we're left with the unit gram. And we can do this by simply multiplying by the molar mass, like this, so that we have mole divided by mole, which is the same as 1, so it cancels out. And now we're just left with X times molar mass with the unit grams. So now we just converted moles into mass by multiplying with molar mass. If this is the case to go from moles to mass, the opposite must be case to go from mass to moles. So let's confirm this. Let's say we have X grams of something and we want to convert this into moles. So let's divide by molar mass and see what happens. Now we see that the unit gram cancels out, so we're left with X over molar mass with units per mole. And just the same as last time, this turns into X divided by M with the units mole. So we now see that we converted mass into moles by dividing with molar mass. Let's sum up what we have learned this video. So if we make a diagram where we have particles here, moles here, and mass here. How do we go from particles to moles, and moles to mass? And how do we go from mass to moles, and from moles to particles? We learned that if you want to go from particles to mass, you have to divide by Avogadro's number. And if you want to go from moles to particles, you do the opposite, which is to multiply by Avogadro's number. And we also learned that if you want to go from moles to mass, you have to multiply by the molar mass. And if you want to go from mass to moles, you have to divide by molar mass. For the sake of remembering these formulas, we can go through some shorthand notation. So the notation for moles is N, mass is M, and molar mass is a uppercase M. And usually in reactions, if you have moles of something, you would write N of element X and mass of element X and molar mass of element X. The important formula to remember here is how these three quantities relate to each other, and they do so by the formula N equals mass over molar mass. And I think this is the formula you should remember for the rest of the IB chemistry course. Let's recap this video by going back to the original equation in the motivation for the mole and see if we can solve it. So in the original equation we had compound A reacting with compound B to form AB. Let's now say that compound A is magnesium oxide and compound B is carbon dioxide, and these two reacts to make magnesium carbonate. let's suppose we want 84 grams of magnesium carbonate. So mass magnesium carbonate equals 84 grams. The first thing we have to do is define the molar mass of magnesium carbonate. So how do you do that? The molar mass of a compound is the same as the molar mass of the atoms, the constituent atoms added together. So for this example, I'm gonna use the molar mass to no decimals for simplicity. Now, if you look at the periodic table, we can see that the molar mass of magnesium is 24 to no decimal places, and carbon is 12, and oxygen is 16. Now, we see that we have 3 oxygens, so we have to multiply this by 3. And if you add all of this together, you get 84. So the molar mass of magnesium carbonate is 84 grams per mole. The next step is to find how many moles of magnesium carbonate we have. So now we use the relation N equals M over M, where N is moles, small m is mass, and big M is molar mass. And we see that we have 84 grams over a molar mass of 84 grams per mole, which becomes 1 mole. So moles of magnesium carbonate equals 1 mole. Now, since this is a 1-to-1 reaction, this means that the moles of carbon dioxide is also 1, and moles of magnesium oxide is the same. So now we just need to figure out how many grams of magnesium oxide we need and how many grams of carbon dioxide we need. So just in the same way as previously, you can find that the molar mass of magnesium oxide is 40 and that the molar mass of carbon dioxide is 44. And now we can rearrange this equation so that it becomes mass equals moles times molar mass. And if you use this equation now, we can see that the mass of magnesium oxide needed equals moles, which is 1, times the molar mass, which becomes 40 grams. So mass magnesium oxide needed equals 40 grams. And this is the same for carbon dioxide. Mass becomes moles times molar mass, which is 44 grams. So the mass of carbon dioxide needed equals 44 grams. And this becomes the answer for the originally proposed problem. So now we see that this problem was indeed solvable with the mole concept. More on calculations in chemical reactions is going to be covered in a future video, but for now we've covered the mole concept. In the next video we're going to cover empirical formula. See you then.